At the bottom of the globe sits a slab of ice roughly the size of France. This is the Ross Ice Shelf, a towering expanse of frozen water several hundred feet thick. Because of its massive weight, this shelf acts as a physical barrier, stopping the continent's inland glaciers from slipping into the sea. If this plug fails, the ice behind it will surge into the ocean, unleashing a rapid rise in global sea levels. Antarctica is currently heating up, and as the ice melts at an accelerating rate, this barrier is becoming increasingly vulnerable. Satellites orbiting above provide a view of the surface, but they cannot show researchers what is happening deep inside the ice itself. To try and track internal behaviors, a team of researchers in 2014 buried 34 seismic monitors deep into the snow. Observing the internal state of this 193,000 square mile block is how scientists determine when a shelf is moving toward a tipping point. The data captured by those sensors revealed something unexpected: a continuous, invisible vibration echoing through the ice. It was a low-frequency seismic hum, vibrating at a pitch completely inaudible to the human ear. When researchers sped up the recordings to a frequency we can actually hear, they discovered the ice produces an eerie, mournful drone, similar to the sound of a swarm of cicadas in late summer. This hum is generated by environmental forces. Continuous winds blow constantly across the flat Antarctic landscape. As these gusts whip over massive surface snow dunes, the friction and airflow turn the icy ridges into acoustic generators. The interaction between the wind and the dunes sends physical vibrations plunging deep into the thick ice sheet below. These forces essentially transform a 193,000 square mile slab of ice into a massive acoustic instrument. This sighs constantly in response to the environment. A sudden drop in air temperature or the arrival of a severe storm physically alters the ice's acoustic properties. Even the presence of meltwater on the surface changes the frequency of the hum traveling through the shelf. Internal fracturing or shifting layers of snow further tweak the pitch of the vibration. Melting ice, violent storms, and shifting snow all create distinct, measurable seismic signatures. Because the melee shifts based on the shelf's physical state, the sound acts as a real-time map of the ice's structural integrity. Glaciologists are now actively reading this audio stream as a diagnostic tool. The acoustic data allows researchers to monitor what is happening beneath the surface in real time without the need for visual confirmation. Instead of waiting for a satellite to pass overhead and photograph the surface, scientists can track the health of the ice second by second. This continuous stream of data reveals internal shifts as they occur. Researchers listen specifically for the acoustic signatures of the shelf beginning to fracture and disintegrate. Monitoring this steady heartbeat gives researchers a vital way to track the stability of the shelf as the climate warms. By listening to the shifts in pitch and frequency, scientists can identify the exact seismic patterns that precede a total structural collapse.